Good morning or good afternoon from wherever you're calling from, and thank you for joining us for a webinar to discuss in-situ remediation technology or alternatives to dig and haul. This is Ignacio Berit with the Center for Creative Land Recycling, and before we start, I have a few housekeeping items to go through and a little intro to speak there. You may download the presentation by the link to the console on the right. We will not be, all callers will be on mute, but you can enter any questions also in the dialog box on the right. And we will take any questions as they come up and at the end of the webinar. A little bit about CClear. We are the only national nonprofit dedicated to recycling land. We conduct webinars and workshops to educate stakeholders involved in land reuse. CClear is a technical assistant to brownfields grantee under the U.S. Environmental Protection Agency's Brownfields program. Under this grant, CClear covers EPA regions 2, 9, and 10, and our TAB partners are New Jersey Institute of Technology and Kansas State University. TAB providers serve as independent resources to state, regional, county, tribal, and local government, and nonprofits attempting to clean up and reclaim brownfields. We're going to pull up a map now, and please start, figure out where you are map. Well, before I get to the map, this webinar is one of many CClear has done over the past year. In 3 weeks, we will have a webinar on Phytoremediation. And for those interested in the EPA assessment, cleanup, and remediation, a revolving cleanup grant, that will be released soon, and the TAB providers will be hosting a webinar. Now, please take a look at the map and try to figure out where you are on that map, and we'll be asking a few polling questions. First question is, what sector do you work in? So the poll is open, so please give everyone 5 seconds to reply. And the results are, we have more than half of you are in the environmental sector. That's new. 17% other, 10% real estate and development. People, some in planning and some in engineering and geology. The next polling question is, what EPA TAB region do you work in? And the results are, okay, most of you are calling in from regions 2, 9, and 10. We have about 20% from the Midwest and South, and 3% from the Northeast and Southeast. And the last question is, how long have you been in the land reuse field? All right, and the results are, okay, mostly under 5 years, and a few with quite a bit of experience. So there's the, I don't know what gap you call that. It's like a U-shaped graph we have here. Very interesting. For our next slide. So for today's presentation, we have presentations from Arul Ayyaswami from TetraTech in Philadelphia, and Joe Muzzio with Reterro in Livermore, California. And I will be your moderator. As I had said, we will be taking questions as they come in, and we will take the bulk of the questions at the end. Our speakers have decades of experience in land actually in remediation, and really finding alternatives to dig and haul. Dig and haul is very disruptive to neighbors and the environment, and this is the main reason why we're having this presentation, is to exemplify the other alternatives and how much more efficient they are. So with much further ado, next slide, I will hand over the floor to Joe.
Thank you, Matthew. So today, Arul and I will be talking about soil and groundwater remediation alternatives in lieu of dig and haul, pump and treat technologies, which are pretty much the classic go-to technologies for some brownfield developments. So for today, I'm going to be looking specifically at soil remediation alternatives. And first, we're going to look at an overview of dig and haul, so we're all on the same page about the advantages and disadvantages of dig and haul. And then we're going to look at, I'm just going to skim over some of the most common on-site soil remediation alternatives. And we're looking at not just in-situ remediation, which is subsurface work, but we're also looking at some ex-situ soil remediation, on-site soil remediation treatment alternatives. And then Arul's going to step in after that and get into more detail about some of these in-situ remediation alternatives. And then at the end, I'm going to talk a little bit about the evaporative desorption technology, which is a proprietary ex-situ soil remediation technology that my company uses. It involves heated airflow through soil to volatilize contaminants and remove them from the soil so you can reuse the soil on site. And I'll follow that with a case study of one of our larger projects where we actually did a screening level life cycle assessment to show the difference in environmental impacts between a theoretical dig and haul scenario at the same site and the actual impact shown by our on-site remediation. So to start, I think everyone knows what dig and haul is, but just to define it, it's an ex-situ soil remediation alternative which involves excavating the contaminated soil from the ground, placing that soil into trucks, and then shipping those trucks off to licensed landfills. So they're going to be shipped as non-hazardous waste or as hazardous waste. The pricing can be expensive, and obviously it's dependent upon how far away the landfill is from the site and what kind of waste you're disposing of. If it's hazardous waste, it can be quite expensive, and non-hazardous would be less expensive. So first, the advantages. There are some advantages to dig and haul. It does provide for the complete contaminant source removal, and in doing that, by digging soil out of the ground, you're opening it up at excavation, which allows you to visually evaluate and chemically analyze the soil to determine if you've removed all the contamination you need to remove. It also quickly eliminates any potential human health exposure pathways like thermal contact, ingestion, and vapor inhalation. And this is good because it can help implement a quicker property development. You can get rid of that immediate risk of human health contact with shallow soil. It's most feasible for removing soils that go down to about 15, 25 feet. If you go deeper than that, you're going to have to use specialized equipment, and that brings the cost up. So it's definitely more of a shallow soil contamination remediation alternative. And then finally, it does allow typically a quicker soil closure from the regulatory agency because you're able to remove all the contamination that poses the most immediate risk, and that would allow a quicker redevelopment of the property while you're still dealing with the deeper contamination and deeper soil and groundwater. Now the disadvantages, it can be more expensive, much more expensive than in-situ and ex-situ on-site treatment technologies. It goes on a case-by-case matter. It definitely has a negative impact to surrounding neighborhoods. When you're shipping soil off-site with trucks, you're going to have increased traffic and safety hazards as you're shipping trucks out with the dirty contaminated soil, and you're bringing in clean imported fill to backfill the excavation. You're also having an increase in greenhouse gas emissions from the trucks, diesel trucks, as they go through the neighborhoods. And then finally, there will be some damage potentially to community infrastructures road damage due to trucking, dust, and just road wear and tear, basically. Finally, when you haul soil to a landfill, landfills have a finite storage capacity. So you are depleting a resource that it has a finite life to it. So you have to consider that too. And then when you're bringing imported clean fill in, you're also drawing on a resource to supply clean fill. And then finally, under the Resource Conservation and Recovery Act laws, a responsible party that owns a contaminated site has cradle-to-grave liability for that contamination. So there is generator liability when you dispose of soil in a landfill that could come back to bite you, basically. If that landfill were to have some environmental impairment, they would look to everyone that's put their soil in that landfill that could be contributing to the contamination, potentially. So the EPA Brownfield Support Center has provided a list of quite a few alternatives for soil and groundwater remediation. Soil alternatives are listed here, and there's a number of those, and we'll go through some of these. That can be divided into in-situ and ex-situ technologies. So now we'll just briefly look at some of the in-situ technologies, their advantages, disadvantages, and then some of the ex-situ technologies. So in-situ, there's a number of them, and Arul's going to talk more in depth about these, but basically, these are the most commonly used in-situ soil remediation technologies. Now, they're dependent on the contamination type. If you're treating a volatile contaminant that can volatilize and degrade, you're going to select alternatives like soil vapor extraction, which volatilizes the contaminants and removes from the soil. You're going to look at adding amendments to the soil for enhanced biodegradation or chemical oxidation of the contaminant. And then you can look at in-situ thermal remediation alternatives, which again use electric or steam heat to volatilize the contaminants and remove them from the soil. And then if you're dealing with an inorganic contaminant like metals, you can do stabilization or mixing of the soil in the ground to stabilize the contaminant and prevent it from leaching to groundwater. The advantages, there are a number of advantages to in-situ remediation. The soil remediation is completed below ground, so there's no significant surface disturbances. And it does work well at depths greater than feasible with any excavation. So if you've got deep contamination and groundwater contamination, an in-situ approach is typically the way to go. It's often less expensive than ex-situ remediation technologies, primarily because of the bug, you're not impacting ground conditions. The disadvantages, it can often be slower than an ex-situ alternative. And then finally, probably the biggest disadvantage is success is controlled by the heterogeneity of the contaminant distribution and soil type. That is, you're relying on interpretation of subsurface conditions based on a limited number of borings or data that's collected in the subsurface to design a system that can effectively remove all contamination. And then you have to go back in and do confirmation soil sampling to confirm that you've removed all contamination. So those things can slow the process down, and you can never be assured that you've entirely removed the extent of contamination. Ex-situ remediation with on-site treatment, similarly, it's controlled by the type of contamination. If we're dealing with volatile organics, you can dig the soil up and create biopiles and add amendments and do enhanced biodegradation. You can mix chemicals into the soil to promote oxidation of the contaminants. And then you can also use low or high temperature thermal remediation, which these basically was used quite a bit in the past, in the 80s and 90s for remediation. It was using rotary kilns to basically volatilize and even combust the contamination and before putting it back into the ground. The rotary kilns have not been used as extensively these days, especially in California due to air permitting regulations. And then finally, evaporative desorption is a subset of thermal remediation, and that's what I'll explain later, but we use low temperatures and heated airflow to extract the contaminants advantages, obviously, when you're digging soil out to treat it, you're going to get complete removal of the contamination. So again, you can see visually that you remove the entire extent of the contamination. You're not dealing with the heterogeneity issues that you do with the subsurface, because by digging the soil out, you're homogenizing the material, and you can blend it and treat it to remove all the contamination. Most of the ex-situ technologies are relatively quick compared to the in-situ technologies. Not always, but in most cases they will be. And you can also combine an ex-situ technology for shallower soil with a deeper in-situ technology for deep soil and groundwater. And then the disadvantages are somewhat limited by depth. But then again, you can, as with dig and haul, you can treat soil on site and put it back in the hole after it's been cleaned and proven clean, so that you can expedite property development. So that's an overview of the in-situ and ex-situ on-site remediation technologies. Now I'm going to turn it over to Arul, who's going to go into more detail on some of these technologies.
Thanks, Joe. Yeah, thanks, Joe. And can you all hear me? Erica, can you hear me?
Yes, we can hear you.
Good, thanks. And this slide talks about, the evolution of remedial technologies. About 20-25 years ago, whenever there is a contamination, if there's a soil contamination, the only technology we knew is excavation and disposal off-site, which is dig and haul. And if the groundwater is contaminated, what we do is pump and treat. So we all know, as Joe really clearly explained to us, dig and haul is pretty expensive, and it's got a lot of other issues as well. And pump and treat has got its own inherent problems. So pump and treat, by doing the pump and treat contamination, you're only removing about 5 to 10% of the dissolved phase. And because of the asymptotic behavior of the pump and treat, it takes a long time to remove the contamination, and you'll be running the pump and treat for 10, 20, 15 years. So it's not really feasible, and we came up with some innovative in-situ technologies like a mass transfer technology, like air sparging. And air sparging is essentially, we'll talk about the details of air sparging later, essentially injection of air below ground to strip or aerobically biodegrade the contamination in the saturated groundwater. As Joe said, soil vapor extraction, we'll see the details of the SVE. Soil vapor extraction is for soil for both chlorinated and petroleum hydrocarbon soil. If the soil geology is good, this may be a very good technology to remove the mass in the subsurface, in the soil, instead of excavation and disposal. Then came the third technology, said, hey, what happens if a plume goes off-site? We need to contain it. Before, people are doing a pump and treat system to contain it. Now there are other technologies, like if it's a shallow water table trenching, or a deep zero-valent ion. If it's a chlorinated hydrocarbon, you put ion to treat the chlorinated hydrocarbon and treat it at the clean water off-site. Or a reactive wall and reactive gate. It's called a funnel and gate system. Essentially, you let the water come down gradient and use a funnel and gate system to treat the water to go off-site. Then came in-situ mass reduction techniques. Like when I say oxidizing, I'm talking about injection of hydrogen peroxide, potassium permanganate, or sodium persulfate with an oxidizing agent. Inject them into the groundwater, which is a contact sport, so that you can treat the contamination into innocuous substances like CO2 and H2O. Simple. Only thing is the contact force is pretty immediate. The oxidation potential can be as far as minutes to hours and days. It's pretty, if you can get the contamination and the chemical in contact, it's pretty fast. In-situ reductive technology is for chlorinated hydrocarbon. You induce reducing conditions to stimulate the anaerobic degradation of contaminants. We'll see the details of it later. The last item is what I call is the best system is no system at all. Essentially, using the natural biogeochemical analysis, a monitored natural attenuation system, you monitor the groundwater, show to the regulatory agency the plume is shrinking, plume is not going offside. You can model them and show it's going to take so many years to remediate without any intervention, without doing anything else. So that's a monitored natural attenuation. And why the evolution of technologies came from extraction to M&A, but in the next slide, we'll talk about the cost of analysis of all these different technologies. Erica, can you move to the next slide, please? And this slide kind of shows the capital cost, which is in green, and O&M cost in blue. If you look at the extractive techniques like the pump and treat system, when you have the operation maintenance cost and capital cost, it's pretty high. When compared to in-situ technologies, when you combine these in-situ technologies with the capital cost of O&M, is fairly reduction compared to extractive technologies. And this not only because of cost, number two, you're able to remove the contamination faster and get closure faster. And also in situ, you don't have any moving parts outside. You inject the substrate, depending on the type of substrate, how often you do, and all the reactions or even bioremediation occurs below ground. It's pretty passive in that way and sustainable compared to the pumps and motors and controls and discharge you have for a pump and treat system. So this is not only cost, but you can even achieve the remediation site closure established by the regulatory agencies within a reasonable amount of time. Next slide, please. And this is a remedial hierarchy, what I say, between cost and complex. The monitored natural attenuation, as you know, you just monitor them. The cost is low, essentially sampling costs over a period of time. Then as it gets to mass transfer, which is air sparging, soil vapor extraction, you are transferring the mass from the liquid phase to the vapor phase. It's going to cost a little bit more. It's a little complex. There's some design has to be done. And biological is the next complexity because you need to induce the reducing conditions. You need to make sure, you need to understand the groundwater velocity regulation, how far you need to go, how often you need to treat it, what type of substrate you need to use. The chemical, the cost is higher and a little bit complex because we need to consider all aspects, including health and safety, but it's really good. You can do it faster, but it's a little bit, the complexity is a little bit more than biological and also the cost. Next slide, please. This is a typical cross-section. What is soil vapor extraction? It's pretty fairly simple. You have an extraction well with a slotted pipe in the soil, in the contaminated area. Using a blower, you extract this air. When you do that, what happens, the airflow occurs from top to bottom. It strips the contamination because of the vapor pressure, Henry's law constant, all the chlorinated and hydrocarbon can be stripped. If it's aerobic, if it's the benzene, toluene, ethyl benzene, it can enhance the aerobic bioremediation in the air as well. So it's a very simple technology. If the geology is right, if it's more permeable, it's faster to remediate. It's a little bit less permeable, it won't be that fast, it'll be medium, and we can look at the geology and see how it works because of the mass transfer with the geology and the complex compounds in the subsurface. Next slide, please. The other technology is in-situ air sparging. This is essentially a technology, if the geology is right. You inject air below the water table and you strip the contamination. And if it's petroleum, you aerobically biodegrade the contamination. So what happens, the stripped contamination comes up in the vadose zone in the soil above the water table. It's been extracted by the blower, which is an SVE system. And because of the concentrations are higher in the vapor phase, depending on the concentration, depending on the place, which state we're doing, we need to have a vapor phase treatment to discharge to the atmosphere. This is a basic concept of air sparging. Next slide, please. And for example, if the petroleum hydrocarbon, what does it happen? If you look at the x-axis, the contamination with the increasing density, you have gasoline, which is the vapor pressure is pretty high and highly strippable compound, to all the way to number 6 fuel oil. So when you look at it, the stripping and volatilization for gasoline is pretty high. Only about 20% is biodegradable because it's all stripped. But the more denser you go to JP4, to diesel, and number 6 is more of biodegradation rather than stripping and contamination because of the Henry's law constant and vapor pressure is fairly low. Next slide, please. And this is an in-situ air sparging. The bottom line of sparging to be successful is if you inject the air below ground, you should be able to remove in the extraction well soil vapor extraction. If you can remove all the strip contamination, the vapors, then this is a viable technology. If we have geology different, the different layers of clay and sand or clay layer about it, if you're not able to extract in the vapor zone or a soil vapor extraction, this is not the right technology. We have to make some modification to the technology. So geology is very important for sparging. If it's a rule of thumb, if it's more permeable, it's very easy to treat. If it's heterogeneous, it's complex, we need to look at other types of sparging to take care of the contamination. Next slide, please. And this slide, this is a modification of air sparging. For example, if you have a geology with different layers, clay layer and sand, what is known as in-well sparging. The main difference between conventional sparging and this, all the stripping happens in the well. Essentially, there are two screens on the bottom and the top. You have a injected air, strips the contamination. It acts like an airlift pump, brings the water up, strips the contamination, and puts it back. And it acts like an in-situ biological reactor. Very efficient. It can go pretty deep. But you can make some modifications to conventional sparging to have this. This is a simple schematic of in-situ air stripping or in-well sparging. Next slide, please. So if you have a geology, it's pretty tight. The hydraulic conductivity has got a lot of clays in it. The only form of remediation is excavation and offsite disposal. This technology may be a viable technology because this applies a very high vacuum. Next slide, please. When you look at it, the basic fundamental concept of vacuum enhanced recovery is you apply a very high vacuum to closer to using a liquid ring pump or about 16 to 18 inches of mercury blower. When you apply that, what happens is, because it's low permeable, only very little water comes out. Then the whole soil, there's no water, so you move air through the former saturated zone and you aerobically bioremediate or strip the contamination. The mass removal in the vapor phase is 5 to 10 times more than a conventional water, because water, you don't get that much water because it's low permeable. And the mass you remove in the vapor phase is quite a lot compared to water. And this is very aggressive technology. It may cost a little bit more money, but it's very effective in removing the mass in a low permeable formation. Next slide, please. This is just a schematic of of a vacuum-enhanced recovery. If it's the shallow water table, you can go with a drop tube scenario. If it's the deeper water table, you can go with a pump and a tube to apply a vacuum so that it goes to the knockout tank and goes to the vacuum pump and then discharge with or without off-gas treatment, depending on the concentrations of the vapor being discharged to the atmosphere. Next slide, please. See, we have seen different kinds of technologies. Now, we're going to talk about the injection-based technologies, like either oxidation or reduction. The key thing in an in-situ injection-based remedy is delivery, delivery, delivery. You need to deliver the substrate or the reagent to the contamination. So if we can deliver that, we know the technology works. We know the chemistry works. We know it is biodegradable. But you got to get the substrate to the contamination. When you can do it, when you can create a reductive zone so that the contamination gets reduced, if it's a PCE, goes all the way to ethane. If it's oxidation, gets oxidation to CO2 and H, that's fantastic. That is a key objective in an injection-based remedy. And the whole idea can be different. It could be a source area treatment. It's a interception of the contamination going offsite. And these contamination, if it's a chromium, you can, as Joe pointed out, in-situ stabilization. You can inject a reducing environment for an hexavalent chromium to be precipitated as a chromium hydroxide. The solubility is very low. It doesn't come back. It's a pretty neat technology. The final end product is a harmless end products. So that's the whole objective of in-situ remediation. Next slide, please. As with any remediation, you need to know what type of delivery, what type of drilling methods you need to do, what type of injection pressure, all can be developed during the design of the injection system. And what type of reagent? Sometimes you inject something, it is there for 6 months. Some of the reagents like emulsified oil, it stays there for 6 months. Some of the soluble compounds like sugar, molasses, or even lactate, you need to do it periodically. So those are the things you need to really understand when you're doing the injection. Next slide, please. And this is, under reduction PCE, which is 4-ring chlorinated compounds. You come all the way to PCE, TCE, DCE, vinyl chloride, and ethane and ethylene. And this is a basic concept. You remove chlorine every time by doing the injection of a substrate, reducing into the groundwater. This is a basic concept of enhanced reductive dechlorination. Next slide, please. And I just wanted to bring it, there's going to be a detailed presentation by Ziegler in a couple of weeks on phytoremediation. And phytoremediation can be used for removal of chlorinated hydrocarbons, petroleum hydrocarbons, either shallow or deep. If it's deep, there are modifications you can make, or even like a containment. Or even to prevent water, if it's the landfill, we have designed phytoremediation to prevent water into the landfill. So like trees like willow trees, all these things can be used, and poplar trees can be used to absorb the moisture content. Next slide, please. Okay, I want to bring in, this is all the technologies we talked about. I just want to kind of talk about some of the investigation things briefly, how we can bring the investigation things. As you know, brownfield is very complex. It is various parties involved: EPA, the regulatory agencies, the client, the lender, consultant, buyer, seller. So when you have a lot of parties involved, there's a lot of uncertainties, a lot of liabilities, and speed is an important thing because you need to transfer the contaminated property into a money-making machine, So for everything else, we need innovation, even from the remediation point of view. Even for investigation point of view, can we, when you do investigation, can you keep remediation in mind? That's called a remediation-focused investigation. Then what is the end plan? What is the remediation? Everything else should be planned for a brownfield remediation. That is very important. And upfront, you need to know what we're doing and where we're going. Next slide, please. And if you go with the initial site characterization, like well by well, it's going to be really expensive. So there are some ideas I want to kind of talk about it, how we can do it with some of the innovative ways of collecting data. Then we can go and confirm it based on the initial data. Hey, this site, we know the vertical extent of contamination. It doesn't go more than 20 feet or 50 feet below ground. So we need an idea. So there are some innovative investigation methods we'll see in the next few slides. Next slide, please. And for any brownfield remediation, we need to know what we're going to build. Are you going to build in a school or an office complex or a strip mall or a big end office complex? So once you know the goals in mind, we can focus the remediation based on the development plans, where we're going to put the building, where we're going to put the investigation wells, or even the remediation wells. Those are the things which is key for the remediation-focused investigation. Next slide, please. And this is what I want to talk briefly about, is a rapid characterization or investigation technologies. There are technology available to really find out, hey, where is the contamination? Is it, what is the lateral extent of contamination? What is the vertical extent? So there are field and data analysis can be done to visually understand where is it, how deep it is. Can you go to the next slide, Erica? And these are, there are different characterization technologies like LIF, which is a laser-induced fluorescence, rapid optical screening technique, membrane interface probes, nothing like a PID. You kind of drill down deeper and deeper, and you have instantaneous readings of PID in the ground. Tells you where the concentration is. Then you can go back with a well to confirm that, but it tells you it's not only the concentration, the other GIS information. You can plug it into the map and see a very nice picture where the contamination is. Can you go to the next slide, Eric? This is a shot of a site plan. If you see the red plumes in the map, this is the concentration going into the site and off site. Next slide, please. This slide shows the vertical distribution. If you look at the red on the left corner, is the VOC distribution on the higher probability. It gives you an idea by looking at it. Hey, it is about 40 feet deep or 50 feet deep. So we know the extent. It may not be perfect, plus or minus 20%, but it gives you an idea where the contamination is gone. Next slide, please. And this is from the development point of view. If you have a contamination pretty shallow, but 10 feet, as Joe pointed out, there are a lot of above ground things we can do. This is kind of an in-situ soil blending. Essentially have a Lang tool, which an excavator is got a mixing tool in it. You can mix the soil at the same time inject the oxidation and lime into it and mix it. So the concentration pretty fast. As I said, oxidation is very fast. So we add about 100 ppm of total VOCs to the soil and daughter products to less than 0.1 in about a week. So it's a very instantaneous tool doing it, but it all depends on where the concentration is, how deep is the soil. This gives you one case study of soil blending. Next slide, please. And this is a case study of a very permeable formation, a 250-acre site, which was used as a former aircraft facility. The contamination consists of PCE and TCE, and it's in the shallow groundwater and also in the soil. This is, next slide please. Next slide please. Yes. So the part of the work is to do some remediation and also do a demolition, removal of the PCB, which is polychlorinated biphenyls, and asbestos, some mercury lamps, lead brick. It's got everything, the whole building. So we cannot took over the building demolition, PCB removal, all the soil, all the paint removal in one contract. Can you go to the next one, please? And this is the previous site conditions to the left. It was a plane hangar, it's a little plane, an aircraft facility, and everybody has to go to the public meeting, so the people are really worried about what we are going to do, what kind of soil excavation we're going to do. This is a shot of the building demolition and the asbestos removal. And this is a shot of a air sparging and SV system. If you look at it, air sparging is the injection of air below ground. SV system is drawing the air with the blower end. And there's a tank which shows the storage of the chemicals, storage of water, anything else to be done on site. Next slide, please. And the end product is a strip mall. So it all depends on what we are trying to do, what is the end goal, and so this is the remediation done in but 2 years, you know. Finished the remediation, got the closure, and it was easier because the soil is pretty permeable formation. You can do air sparging and you can extract the mass in the warehouse. Joe, can you take it from here?
Thanks, Arul. Yeah, I know we're running out of time here, so I can make this brief, and I believe everybody on this webinar has access to these slides, so I will go through them quickly, and you're always welcome to call me if you have questions. Anyway, first I'm going to introduce you to evaporative desorption, and then I will get into a case study where we actually looked at the sustainability of our process compared to a dig and haul scenario. So first, this schematic shows how our system works. We treat basically 20 tons of excavated soil at a time. We place the soil into bins in the desorption system, and then we inject electrically heated air through the soil to volatilize the contaminants and remove them. The volatilized contaminants are vacuumed out the back end of the unit, and they are destroyed by a catalytic oxidizer, thermal oxidizer, or they're captured on carbon. Now this is one of our units. This holds 2 bins. You can see on the right, that's a bin that holds 10 tons of soil, and there's another one on the left. That equals about 1 truckload of soil. So when we excavate soil from the excavation, we put it in our bins and put it in this unit. And inside each of the bins, we have a vapor extraction line. So we apply a vacuum to that vapor extraction well you see, which draws the heated soil or the heated air through the soil column to volatilize the contaminants and bring them out the back end. Our systems are all electric, which is very sustainable. They can run off grid power or a diesel generator if necessary, but if the project's big enough, we typically like to run off grid power. So as you can see, there's no moving parts. We don't generate any dust. There's no NOx or SOx emissions because we keep our temperatures low enough that we're not forming any of those gases. This is our typical unit. It's got a fairly small footprint. A single unit on site will take up about 45 by or 50 by 75 feet. We can add multiple units as needed to treat more soil, because each unit will treat anywhere from 100 to 200 tons of soil per day. And if you need to increase production, we can treat up to, we can add 2, 3, 4 units on site to keep up with the excavation production required. Obviously, the benefits are that it eliminates landfill costs and liability, and we've seen that we have no significant environmental impact compared to a dig and haul alternative. So this is the process starting in the upper left-hand corner. You fill the bins directly from the excavation. You drop down to the lower left-hand corner. We weigh each bin because we charge on a price per treated ton, so we record all the weight. We load into the bin, and we start our process where we're injecting heat into the soil. For 20 tons or about 1 truckload of soil, it takes anywhere from an hour and a half to 4 hours to clean the soil to whatever the cleanup goals are, depending on the contamination type and the cleanup goals. From there, we empty the soil out and let it cool, and then it's tested and ready for reuse. Okay, so I just want to go over a quick case study. This is a 45-acre former manufacturing plant where we were selected over dig and haul to treat 97,000 tons of soil on site. They selected us over dig and haul based not only on cost, but also the city was limiting the amount of truck traffic that could go in and out of the site. So they were limited to about 15 trucks a day, which was driving the cost of the excavation and the development up significantly. So they brought us on with 2 machines, and we were able to process 97,000 tons of chlorinated solvent, soil and soil vapor. We operated 24 hours a day, and we were connected to grid power. Basically, the results showed that when we were at maximum capacity of processing time, we were achieving about 12,000 tons, or just under 12,000 tons of soil per month, and we treated the 14,000 tons, the 100,000 tons in a 14-month period. By doing so, we eliminated about 8,000 trucks from the roadways. That was 4,000 trucks going out to a landfill and another 4,000 coming back in with clean soil if a dig and haul approach were used. And also we cleaned the soil, backfilled the excavations, and we received a no further action on the soil so they could start development, and that was within 2 years of starting the entire process. So based on that, we wanted to look at how sustainable our on-site treatment process was compared to a dig and haul scenario given the same parameters. And we do have a polling question for you, which is, can't see the question. Does sustainability of a remediation approach affect your decision when working on a project? So it's not required, but it is something that is looked at during the alternatives evaluation for a brownfield development. Next slide.
Okay.
So 83% say yes, 17% no. Very good. So we retained an outside consultant, WSP, to perform a screening level life cycle assessment to evaluate the sustainability of on-site treatment versus a dig and haul scenario. We specifically looked at global warming potential. We looked at primary non-renewable energy demand, and then particulate matter emissions. So the system boundaries were very extensive and very complete. We looked at all aspects of the project, given a dig and haul scenario and a on-site treatment scenario, looking at all the equipment in operation, diesel consumption, electricity consumption, even down to, we were using activated carbon as our treatment method. So we were looking at the environmental impacts of activating the carbon, transporting the spent carbon for treatment, and actually treating the spent carbon. So these, quickly, the results are pretty significant. When you look at the primary non-renewable energy demand, the dig and haul energy demand was an order of magnitude greater than on-site treatment using electrical usage for our system. The next one. You can go to the next one. Global warming potential. This is basically CO2 emissions, and again, it's another order of magnitude, and that's primarily due to obviously the diesel consumption used by the trucks to off-haul the soil versus our electrical usage, which does use some fossil fuels to generate the electrical power. So we do have a bit of a footprint there, but not significantly lower than dig and haul. And then finally, we look at particulate matter, and again, this is primarily due to the dig and haul. You know, the diesel combustion from trucks is significant enough to really increase the particulate matter emissions. So in all, if you look at a summary, just comparing each of these, on-site treatment versus dig and haul, we see approximately 95% reduction in global warming potential between dig and haul and an on-site treatment technology. We see 85% reduction in primary renewable energy demand, and again, and even more, 98% reduction in PM2 emissions. So again, this is a screening level. It hasn't been vetted beyond a screening level approach, but it's pretty dramatic, and it shows really the environmental impact that dig and haul can have on a project. Somebody asked the question of what's the name of the consulting firm. We're Reterro, R-E-T-E-R-R-O, and we're not consultants. We're contractors that own this proprietary technology. Somebody's asked if there's ever been any operations done in Alaska, and yes, we've worked in Alaska. We brought one unit up to Sitka, Alaska, to treat about 500 tons of soil about 2 years ago. And so all our equipment is easily, we can barge it. It's all built on shipping container frames, and so we had no problem trucking it up from California to Alaska and barging it up to the islands of Alaska. Okay, just in conclusion, you know, dig and haul, it's had its place, and it does have a place for certain specific sites, but it's not always the best option. And really what we're trying to get across here is that you should really consider the environmental impacts of a dig and haul scenario and the long-term liabilities that you hold when you do choose dig and haul generator liabilities when you evaluate remedial alternatives. And you'll find that there's on-site, in-situ, and ex-situ remediation alternatives that are as good or in most times better than a dig and haul approach, and they offer significant benefits. It can reduce overall project costs, it reduces air emissions and that overall environmental impact, and you're minimizing any outside issues associated with neighborhood complaints, traffic impacts, and again, it's the long-term generator liability that is reduced.
Well, thank you, Joe and Arul. And I have just a couple of follow-up questions. Again, I'd like to thank both Joe and Arul, who gave really detailed and a good overview for something so complicated. A question for both Arul and Joe is that, are there any kind of cost considerations that say dig and haul costs X number of dollars, and is there, of course, kind of a threshold where people think, well, maybe in situ would be better, worth considering? Joe, start first, and then Arul.
Okay, I was talking to.
Oh, okay, Arul, why don't you go answer first?
Yeah, definitely. See, it depends on when you go to the soil excavation and disposal, and it depends on what type of, is it going to the hazardous waste landfill, is it going to the local landfill, and also the backfill. Are you going to put a backfill which is $20 a cubic yard? So when you combine all of them, and by doing just a soil vapor extraction for the soil remediation, it'll be a lot cheaper. So excavation and disposal can be anywhere from $50 to $60 a ton to all the way to $150, $200 a ton. SVE system is a lot cheaper than that. It'll be even less than $40 a ton compared to the soil. But again, it depends on the type of soil. So it is half cheaper to 80%, so depending on the type of the soil and contamination. Joe, you may want to add something to it, Joe. Go ahead.
Yeah, from ex-situ technologies, that's about right. I mean, it's all very site-dependent, the volume of soil you're digging up to treat on site. But yeah, it's definitely, based on tonnage, it's definitely comparable to a dig and haul approach. And yes, if the soil is hazardous, most on-site treatments are significantly less than hauling the soil to a hazardous waste landfill.
Okay, we have no more questions. I have just one more. So is trade-off really the main trade-off the time that is there a time uncertainty, and is there also a uncertainty as to what the regulator might require after the cleanup is done, such as institutional controls? And again, Arul, you can start, and then Joe.
Yeah, but there are, for example, in the in-situ treatment, there could be some institution controls too, you're right. But in addition to, if there's a confirmation sampling in-situ, if you do a soil vapor extraction or in-situ remedy like mixing and blending, you got to go back and confirm the mass, how much was before, how much is it now. So if you can prove, because of the in-situ technique, that it has removed about 99% of the mass, and I think we are okay. So if you say the concentration is still there, maybe we need to run the system a little bit longer to prove that we are removed. So these are the things we can do to prove that we removed the mass in addition, or we may not need institution controls if we prove that we removed the mass. Joe?
Right. And from an ex-situ standpoint, I think it's obviously quicker, and like I said before, you're able to get rid of that immediate risk to human health by contact with shallow soil. So by digging and treating on site, or doing some kind of shallow soil remediation on site, you can expedite cleanup for at least the shallow soil, so that you can facilitate a site development.
Okay, well, thank you very much, Arul and Joe. That was a great presentation. To our listeners, again, you can download the presentation and information on both TetraTech and Reterro on the link to your right, and you will have more detailed information on their companies and the good work they do. Thank you so much, and please answer our survey. We'll be sending that out shortly, as well as a link to the recording of this webinar. Thank you very much, and see you in a couple of weeks. Bye.